Hello. Yes, thank you very much. Thank you for the opportunity for coming to this conference. It was very interesting for me, although I confess I'm not sure I will ever trust experimental results again. After seeing how much, I mean, I admire this work. As a theoretician, I had no idea there is such a big statistical analysis going on. What I would like to talk about is a solution to a simple, it turned out simple mathematical puzzle that we encounter while training normalizing flows. While revising this talk yesterday, I unfortunately realized that the title lists seem very technical and very boring. But also I realized that I'm the only one will be giving a talk on this topic, which is application of machine learning for lattice field calculations. Although all the ingredients were here already presented, like normalizing flows, Monte Carlo, I mean Markov chain Monte Carlo. So, okay. So before we came to the boring part, but more technical, I hope that you may benefit a little bit from the introduction to something which is called neural Markov chain Monte Carlo. And I will talk about two approaches to this, which were already mentioned in a previous talk, but I will go into slightly more details because we can do it for discrete system like Ising models and for continuous system, and you have to use different techniques for both. I mean for separately, and because we are doing machine learning, which means optimization. I mean finding a minima of some function, and it seems that the only way that humanity can deal with optimizing is by some form of gradient descent. So we need gradient estimators, which estimate the gradient of our loss functions from the samples we have. And yeah, so that's, I will come to this later. And at the end, I will show the results for very simple scalar field theory, which is 5 to the 4th theory. So let's start with Markov chain Monte Carlo. And it starts that we want to simulate probability distribution, and in physics, it usually have this form, exponential form, and this S is energy. In statistical mechanics, this S is energy, and in lattice field theories, this S is an action or a Euclidean version of the action of this field theory. Actually, mostly what we don't have P. We have this, what I call capital P, because it's unnormalized. I mean, what I will stress that we know this distribution analytically. It sometimes is very easy to calculate, sometimes not, like in QCD, but still we know it up to the normalization constant. And we would like to produce, but what we cannot do usually is to sample directly from this distribution. I mean, this phi is for example, is a field. So imagine Ising model like 1000 by 1000 lattice, or lattice QCD, which means like 64 to the 4th lattice. And on every link of the lattice, there is SU3 matrix. So this is phi. And in both cases, in Ising model, the energy is very simple, just sum over all neighbors. But even though we know this probability, we cannot sample directly, which means we cannot produce samples directly from the distribution. So it's done, as most of you probably know, is using Markov chain Monte Carlo, which we generate successive configurations one after another, modifying this slightly. So we have this probability of going from one configuration to another, and if this probability fulfills something that is called detailed balance condition, we construct the Markov chain, and eventually the distribution, probability distribution of those phis would be the one that we want. And usually we have something which is called thermalization phase, because we have to achieve the stationary mode of this Markov chain, and then we can start our measurements. And the biggest problem in this approach is correlations. Because of this, and usually these are very small changes, those things are correlated. Okay, but this was general, but usually, I mean, there are several ways of implementing that, and most popular, and I think one of the most general, you know, just plug and play, is Metropolis algorithm, or Metropolis Hastings, as they call it. So what we do, we propose a trial configuration based on our configuration. For example, in Ising model, we change a single spin. And then we accept these new configurations with some probability, P acceptance. And if not, we leave the configuration as it was. And we move on. And yeah, so that's the result of Metropolis. I mean, that's if this acceptance probability is in this is of this form. Very often this is symmetrical in that sense that going from configuration A to B, the probability is the same as going to B. I mean, proposing a configuration starting from A to B is the same as from B to A. So this thing cancel, and what you have here is that if the probability of the new configuration is higher, we accept it always. If it's not, we accept it conditionally with the probability that is just the ratio of the probabilities. Yeah? So if it's something lowers probability, we still accept it, but with smaller acceptance rates. And so this is a very standard approach. And if you implement it like that, we have this problem. This is something which some small Gaussians, which I wrote here. And you see that we have it's the autocorrelation functions. We measure correlation between successive correlations and you see configurations, and you see that it goes to 0 around 100, which means that only after 100 steps, these configurations are really decorrelated. Actually, it's not as bad as this because the so-called integrated autocorrelation time is the area under this curve, and this is 15 in this case, which means that more or less we have our error is 4 times larger because that's so. And this is one-dimensional example, and if we have big configurations, and we change only this very small part of them, like one link, one spin, and field, then this becomes a big problem, especially around the phase transition. Then these things blows up, and it's called critical slowing down. Basically, I mean, your simulation stops, not in that sense that it stops, but it doesn't produce decorrelated configurations. Of course, one could try to make bigger changes, but then they will not accept it. So there is this tension. If I make bigger changes, I will make less correlation, but not really, because they will be not accepted. So that's general problem, and one could ideally one would like to, for example, generate the configurations which differ very much from the previous one. So idea of the independent metropolized sampler, not a new idea, of course, is to present a new configuration independently of the previous one, with some probability, for a moment unknown, and then we accept it or not. Of course, it seems, I mean, it's crazy because it means that we have to these things to be accepted, it has to be very close. Probability Q that we know how to simulate from has to be very close to the probability that we want to simulate. So it's just changing the problem of simulating from one distribution to finding a close to it. And then what the machine learning comes in. Because we can learn this probability. So, I mean, and that's we all heard for the last 4 days about learning the probability distribution. Although here it's most of the talk concerned going from samples, mimicking a distribution when we have samples. Here we try to mimic a distribution having the distribution. So how we do it, how we train? Yeah, of course we minimize some loss function, and in this, I mean, you can choose several ones, but I will concentrate on the Kullback-Leibler divergence, but which is defined like that. So it's just and it's like, I mean, the definition is the same, but it's slightly different, probably from what was on the previous slides. I mean, previous talks, that the thing we are learning is as a first argument, not as a second. And Kullback-Leibler divergence is not symmetric. I mean, it has this property that is always greater than 0 and is equal to 0 only when these two distributions are exactly the same. Okay, means almost exactly. But it's not symmetric, so it's not really a distance. Yeah, it's a measure of discrepancy, but it's not a distance because it's not symmetric. And another important point, which was already mentioned in a talk, the first talk, is that if we don't have P, we have P unnormalized. So if we plug into the Kullback-Leibler divergence the big, I mean, this unnormalized quantity, after very easy calculations, I mean, we get the logarithm of P, which is Z times P. What you get, what people call shifted Kullback divergence, which is normal Kullback divergence minus logarithm of Z, which is constant, does not depend on the training parameters, so it doesn't matter which function we minimize. But this is a free energy, okay, up to the beta constant and things like that, but it's, let's say, proportional to the free energy of the model, which means that these things is a rational approximation to the free energy. So when we minimize that, we're getting closer to free energy, and that's how we can estimate the free energy. And I think it's the actually more important application of this approach than just generating samples. Okay, so now how do we do it? I mean, how to find a trainable model that is able to generate samples from a probability and provide this probability. I mean, provide the number. And for discrete models, one can use so-called autoregressive networks, which were so let's take example of a Ising model, which was already presented here, but we don't go through the continuous thing, just you work in a discrete space. And then you cannot use normalizing flows, which are continuous. So a project was proposed, it's so-called autoregressive networks, which means that you factorize your probability distribution into the product of conditional probabilities. It's always exact, and it doesn't change anything, it's only the reparametrization, but you can use the neural network to learn those conditional probabilities. So you input a set of spin, and it gives you out these conditional probabilities. If you multiply them one by another, then it gives you the final probability. For Ising spin, it's easy because the output is as a probability that the spin is up. So it's just one number between 0 and 1. If you want to do Potts model, you have to have, for example, 12, like we are doing right now, Potts model with 12 states. You need 12 output neurons for every Potts spin. And so, and how you generate from this thing? Well, that's the Achilles heel of this approach. It means that you do ancestral sampling, which means to generate the first spin, put it in the neural network, get a conditional probability, generate the second spin, put 2 spins back into the network, generate a third spin, and so on, so on, so on. So basically, you have to run your network as many times as you have particles, and that slows down. That's the bottleneck. But before we do that, we have to train it, and the training. And as I said, we don't have any samples here. In a sense, it's unsupervised training, we can call it. So there is this decay divergence that you want to minimize, and you write it like that. It's just expectation of log Q minus log P taken over distribution Q, the one that we are training for. So it means that if we sample from Q, this is just the approximation of the, because it's just average. If phi's are sampled from the distribution Q. So that's the learning goes. We simulate from the from Q, calculate the KL, use the gradient to improve Q, and so on. So we do not train on the data, we train on self-generated samples. Unfortunately, you cannot put this into your let's say favorite neural network auto-differentiation package, because the parameters theta, which weights, enter into the distribution itself, and it's not capturing this sum. And no, you cannot directly differentiate through this. So one has to go back to the exact expression. If we differentiate it, yeah, we get 2 terms. Yeah, the derivative of the first term, derivative of the second term, and after some algebra, you see that what we get here is just an integral of dq over theta, but that's just 0 because integral of q is 1 because it's a probability distribution. So on average, this term disappears, and what we get, approximate gradient, is just this, that we have a logarithm of q, and q is just a function given by the neural network. So this can be easily differentiated by PyTorch, whatever, JAX, and so on. And that's the signal, which is the difference between the logarithm of the distributions we want to have. And this is provided that we sample from Q. And it was already, this name came up once in reinforcement learning, because this form has it's the same form as used in the reinforced algorithm in the reinforcement learning, and it's very intuitive because you take a gradient of Q and you change it, and it for every configuration, and then you see if you are above your probability or below your probability. So, and if exactly the same, you don't change the gradient. So, and what happens, unfortunately, that this gradient has very big variance. It's unbiased, but it's a very great variance. So what people do in these reinforcement settings, they subtract for every batch that we generate before they because the gradient is calculated over like a batch of configurations, stochastic gradient descent. Then we just measure this signal over the whole batch, the average, and we subtract it. And one can show that this second estimator is slightly biased, very slightly biased, because, well, in the same way that the variance estimator is biased because we put in the sample mean, not the real mean. But its variance is 0 if, okay, it's very hard to estimate this variance, but you can do it if you just look at the perfectly trained network saying, okay, we have Q is equal to P, then the variance of the second gradient approximate estimator is 0, and the variance of the previous was, it can be arbitrarily high because it depends on the partition functions. Okay, so now so that's one approach and one estimator. So yeah, I think I will just do the introduction on this talk. And now normalizing flows. For continuous models, even if this autoregressive thing would be very fast, you cannot use them for continuous models. So what's used for continuous model is normalizing flows, and they have been introduced here a lot. It's just not just, well, it's defined by a prior distribution, usually a very simple one like uniform Gaussian, and then by bijection. It doesn't have to be bijection, but if it's not bijection, it's hopeless to invert it and to find the Jacobian. So the configuration we get is just by passing them through the normalizing flow from some distribution, and then we can estimate the probability, calculate the probability by taking the probability of the prior times the inverse Jacobian. And all the normalizing flow are so constructed that this thing is easy to calculate. And that's here, it's a lot of very nice reviews of how you can construct such flows. And now if you write down the Kubernetes divergence in this language, you are integrating over the prior space, over the Z parameter, which does not depend, you don't train it, it's fixed. So it means that you can differentiate through this divergence directly. And what you get is this kind of estimator, and this can be put in your neural network framework, but there is a difference now. It's not the same estimator. It doesn't look the same as the previous one, and has one disadvantage. We are taking the derivative or logarithm of P. P was our distribution that we want to mimic, and this distribution, as I said, is usually given by E2 action. So what we get, we have to differentiate through the action. And for phi to the 4 theory, when this is just polynomial, it's not a big deal. But for QCT, where it's determinant and things like that, it may be a problem. And so this is another estimator, which I cannot tell you a lot about it, because in a sense that I cannot calculate the variance, but just by looking, and what ends up at some examples, I can tell that that variance doesn't go to 0, even if it's perfectly trained. So what's happening here, that in case of the autoregressive networks, we just simulate from Q and then calculate the probability of this configuration. Those things are separated. Yeah, okay, thank you. And with normalizing flow, we cannot, at least in this, let's say, approach, we cannot calculate the probability of a given configuration. If somebody gives us a configuration, we cannot calculate its probability. What we do, we have to generate it from Z, then we know its probability. And that's that's the flow. We at the same time calculate phi and the Jacobian, and then we multiply them. So the question, can we do that? So how can we, having normalizing flow and having a configuration phi, calculates probability? Well, easy in that sense. We invert it, get the Z, and then calculate and the Jacobian. So if we change slightly the flow of the normalizing flow, no pun intended, we just start with a Z and go to the phi of Z. And then we run the flow backward, calculating the Jacobian. It's the same Jacobian as rolling it forward, I mean, inverse one. I mean, and and then we calculate the probability. And here, this dotted line means that we do not calculate gradients. So I said, this is part that gets technical, but my point is that using this thing, we can adapt the same estimator, the reinforced estimator, which was used into autoregressive networks, to this case. And it means that we can do it without differentiating to the action. So, of course, there is slight disadvantage. We have to run the flow 2 times, but actually, it turned out, because this does not propagate gradients, it's much, much faster. So actually, this approach is only 20% slower. Okay, so that's technical. This is how we do it. That's how a very simple, it's an example of very simple normalizing flow that probably everybody who use the exponential distribution use it, because how you generate from exponential, you take uniform distribution and you pass it to the log. And it's one of the simplest examples of the normalizing flow. So I just make this toy example, and I was trying to learn the parameter of the, just mimic the flow. And I know that now I can do it exactly. And you see, that's how is the convergence to a true parameter. And you see this, and you see this variance of 2 of the estimators, which do not have 0 variance when they are perfectly trained. Still the gradient fluctuates a lot. But of course, on the other hand, it's not sure that this variance is a bad thing, because that variance may help us to better explore the space. And here is the variance of the estimator. And you can see that this estimator without action derivative has really 0 variance. And we tested it on the 5 to the 4 theory, which means it's a approximation, discretization of a scalar theory, that we have a real number on lattice side, here 2D lattice side, and the energy is calculated by taking difference from the neighbors, squaring it up, and then we have a mass term, which is just phi square, and we have the interaction term, which is lambda to the 4th. So it's the same university class as the Ising model, and has the same transition from the ordered and disorder phase, but it's continuous, so you can use normalizing flow fields. And to estimate and to measure the measure that is very often used for a quality of this approximation of this probability distribution is this so-called effective sample size. This is the ratio of the true probability to the learned probability, and of course, for a perfect case, it's 1. And then this thing is 1, because the average V square are the same. And if not, it gives you something like how well the things are decorrelated. If it's 1, it means that everyone, we have effective sample, we can use every sample. If it's half, which means basically that we can use half of the samples, which is very good actually, because usually we have to use like 1 of the thousands samples. So, okay, I will spare you the details. This shows, for example, that near phase transition, these things goes only up to the 1/4, which means that we can use one in the 4 configurations, which still is quite good. But it changes with the phase space. So it is comparison of these 2 estimators. So the takeaway mainly is accept this is technical part, but there are different ways of estimating the gradients. And maybe it's known, for example, in statistical community or people working with normalizing flow or making inference, but in no paper on physics I saw that people are using different estimator than the one we just differentiate through everything. So this may be an advantage in some cases. And importantly, You don't have to take action derivative, and it's a slight cost of performance. But what's interesting that these different estimators have quite different convergence properties, and it's not sure which one is better. So unfortunately, it adds up another degree of freedom in your hyperparameter selection. So the gradient estimator you will be using is again another parameter that you can optimize for. As I said, for some region of the phase space, the one converge much faster than the other one. Okay, much faster, like 2 times faster, which is a lot because you cut your training time by 2. On the other case, it was the other way around. So there is no clear cut issues. And maybe I should to mention that this approach, like probably a lot of approaches that were presented here, is a trade-off. It's a trade-off between training time and simulation time. And at the moment, I would say simulation wins. I mean, it's faster to simulate those things than to train them. But people are now trying. At MIT, there is a big group which does lattice QCD, 4 to the 4th lattice, but SU3. And so maybe I just finish by quoting Fiala Shanahan on one conference previously, which said, yeah, but lattice QCD took 4 decades to produce results which people are starting to use. So 40 years ago, I think Kreutz started simulating 4 to the 4th SU2 without fermions theory, and nobody thought it will give an insight into the matter. So maybe this approach is also at some stage help the simulation. Thank you very much for your attention.
Thank you for the nice presentation. Questions?
Yes, so I guess I have several questions, comments, but we can talk about later as well. But my main concern is, at least in our experiments on Bayesian analysis, is that this ESS is very misleading in the sense that it can be very, very close to 1, and yet the posterior is completely wrong. That's because this minimization of, because you're drawing samples from Q, right? And so it's mode seeking, right? This reverse scale divergence minimization is mode seeking. So in other words, the Q can be much narrower than the true P, and you just won't be able to notice this in high dimensions.
Yes, okay, but this is okay. This is not an issue in that sense that, first of all, these things is there is another approach which is called neural reweighting, which you don't do.
It's the same thing, it doesn't matter.
Yeah, no, I mean, it's only that, because then this thing is exact, but you're right. It can be misleading, but we don't care in that sense. We care because it's just a question of efficiency, not of a bias.
No, I'm saying you get a completely wrong answer. And it's very hard to...
No, you don't get a wrong answer because we always correct.
No, you cannot, because you don't know that there is stuff outside.
No. We get a Q. We know, we get a configuration, and we get a Q of 5. That's exact. And then we correct it. So with this acceptance step. And so the only thing bad that can happen, okay, but very important thing is that, as you said, we have the V, which is very big. Then we get stuck. We'll reject the sample, and the autocorrelation time will be weak. So it's a different approach. We are not taking data and somehow modeling it, but what we are doing is exact. The only problem is that it may be theoretically exact, and practically you get stuck because just one of the Qs will be very bad.
Let me give you a simple example. Suppose you have 2 peaks. You discover one through this training. You haven't discovered the second one. You'll never know there's a second one.
You're right. It's a mode collapse, but I'm saying, yeah, it's prone to these issues. Absolutely, absolutely. It's prone to these issues. As long as you have non-zero for every phi q, you're right. If not, yeah,
high dimension,
I'm sorry.
very hard.
No, absolutely. We could discuss it. There are some. There is a recent paper which shows some promises of something that could alleviate this. Yeah, but absolutely. In that sense, if the Q is zero support somewhere, then of course we have big problem.
Other questions? I have a quick one.
Yeah.
Has been there any attempt to use this for a real QCD and not just 5 to the 4th?
With what, real QCD?
Real
Yeah, it's been, I said, I think, I'm not sure. What I mentioned is with fermions, it was used on, there are results on Schwinger model, which show that actually it can better capture the topological sector. It means that it jumps between sector better. And I think that what they are doing now, right now at MIT, is to apply it with fermions. For sure, they did it for U1 with fermions, I mean, Schwinger model, things like that, and they are moving toward the QCD. But okay, my personal opinion is that it's a long way off because the training is very complex. I mean, and there was, yeah, there was a talk a few weeks ago in Germany when Fiala was presenting, and it seems that, you know, it's very ad hoc. I mean, like with machine learning, it's also unfortunately magic. It's magic in the sense that they don't know how you'll scale to bigger lattices and so on. So yes, the attempt is there, and that's the holy grail because nobody cares about any other theory except QCD. But they starting, but they said 4 to the 4th lattices, and the real lattices are simulated at the moment state of the art, like 4 to the 4th. So there is a long way off.
Yeah, and in fact, that's the problem, right? That these normalizing flows, the training time gets really slowed down, and acceptance rates get very small for larger and larger lattices, and it's not obvious at all that this is going.
No, absolutely, absolutely. I agree. I mean, I must confess that I'm also a little bit mathematician, so I like to play. I mean, there was this puzzle with saying why, on one case, on one side, for Ising model, we do not have to propagate to the action, and why here we have to propagate. And so there was this small puzzle, but I'm very skeptical. But what is nice and is this variational thing. Of course, we can miss some things and so on, but still it gives you some bound on the free energy, and it's very hard to do numerical.
What I'm saying is the training times get very, very long for large lattices.
Yeah, for sure. I mean, there are several advances and so on, but I agree absolutely. I think the variational thing is nice, and probably it's a long way off before it gets, if ever, but we don't know that. I mean, like, you know, but they knew that it's going to be, I mean, people say,
Okay, so I think we need to move on. So let's thank Piotr again.